pleasure to introduce the famous marathon runner, Corinna Cortes. She's also the head of research, New York research of Google.
Yes.
And received her PhD her master's degree from Bohr Institute in Copenhagen and PhD from the University of Rochester. And she has many basic papers on rational kernels, together with Marianne Mori, and she's going to talk to us about rational kernels, the general machine learning framework for the analysis of text, speech, and biological sequences. Corinna.
Thank you so much. Thank you for inviting me. I'm very happy to finally have made it down to here. Thank you for the introduction also. Yes, the title of this tutorial is Rational Kernels, a general machine learning framework for the analysis of text, speech, and biological sequences. And it's primarily joint work with Marianne Mori that I think maybe most of you already know from his work in FSTs, and Patrick Hafner at AT&T Lab. So there are other co-workers that I've had along the path, and I'll mention them as we go along. Now they said a picture can be worth a million words. So what I'll start out with is showing you a little picture or a little illustration of the data that we've had to deal with. Actually, it's not a picture, it's a sound bite. Maybe I should have hooked up some speakers if you have that.
There is audio here.
There is audio here.
You may have to test it during the presentation.
I may have to, do you know where I hook it in? We'll try one of these. And there we go. Okay. But anyway, once we get this working, and some of all the other things we're getting working, this is a recording from a customer service line at AT&T, the so-called "How may I help you" customer line, where people call in and complain or they have their issues, and it's our task in real time to find out what problem this customer is experiencing. So,
it's funny, you guys. This one is you guys, my building is the AT&T, I gotta change it up. And business, you got a private balance, it's so much you charge. You always charge tax, and that's what is, this I don't like it. I don't know that. That's what is the service, what is it? Normally charge, normally charge, business charge $22, $9.50, I don't know what.
all right. This is not an easy task, as you can hear. It is obviously a problem this woman has with her service. She wants to have it disconnected. But in real time, figuring out how to route that call appropriately is not straightforward. We have been using support vector machines in combination with these so-called rational kernels, a special set of kernels for variable length input. So this tutorial will naturally fall in three parts. First, I will be giving you a general introduction to support vector machines. This is actually, I should say, joint work with Vladimir Vapnik that I worked with 15 years ago in developing support vector machines. I'll talk about the separable, the non-separable case, give you some theoretical arguments for why support vector machines actually can be expected to be doing well, and tell you how to kernelize them. Then I move on to rational kernels, these special kernels that find their applications in variable length input, and applications like that are plenty in speech and computational biology, so I'll end up with some examples from speech and computational biology. Now, somebody is going to have to give a little bit here, because first of all, Amtrak was late. I have about 60 slides, and that's probably a little bit too much for this tutorial, but I don't know how much you know about support vector machines. So that is maybe a place where we can go a little fast through it. So let me first of all ask you, how many in here have ever trained a support vector machine? That's at least a good. How many wrote their own software? Okay, one road neural software. So there's one that understands what, but actually.
That's for kernel, for the kernel part.
Okay. So otherwise, it's like libSVM. How many use libSVM? Okay. And SVM Lite. Okay. So that's half. I'll always advocate libSVM, but that's just my own personal preferences. All right. So a lot of you have used it, and not a whole lot of you have actually written your own software. So I'll see. Speed me up if I go too slowly, and maybe actually you will benefit from getting a good going through support vector machines, even if you have been using them.
Actually, maybe a good question. I'd be curious, how many people would be able to write down the problem that an SVM trainer is solving? In other words, the objective function and the constraints.
And is that for the soft margin classifier, the one with errors on it, or the one without errors on it?
Well, you might get a different set of hands.
Yeah, so the one with errors on it. Okay. Well, I think we better now know at least a little bit where you stand. So anyway, I assume that you know what a binary classification problem is, at least. I will only be talking about binary classification problem or actually multi-class classification problems. There are also support vector machines for regression problems, SVRs, but that we will save for next year another time. But when you have a binary classification problem in a learning task, you are typically given a set of labeled examples. They are sampled ID according to some distribution. They come with an input vector describing them and a label, which for a binary class conveniently can say to be -1 or 1. A standard example could be that you're trying to classify humans, whether they're male or female. So we have an input vector X describing the person, height, weight, shoe size, hair color. And our task is not necessarily to find a hypothesis that gets the training set right, but a hypothesis that in general, a classifier that in general will get a low error on any point sampled according to the same distribution. Now, for support vector machines, we'll actually restrict ourselves to hypotheses that produce a linear classifier. Now, you can say that is very weak. What can we do with a linear classifier? Not a whole lot. But there's nobody that says we have to stay in the original input space. In support vector machines, we'll typically make use of a nonlinear transformation that will take us to a high-dimensional feature space where we'll perform the linear separation. Now, it is computationally costly, of course, to operate in a high-dimensional space, and that's where kernel methods come in. They provide a closed-form computation of an inner product in a high-dimensional space. So let me give you a little example here. We have our two-group classification problem, and what we're looking for are these linear separators. Functions of the form omega x plus b provides an output, and as classifier, we're going to take the sign of this output. So here we have, in the separable case, two sets of points, and here we have a linear classifier that separates the points. But if the problem is separable, there's not just one line that separates them. There's a whole family of lines here that separates the point. Which one should we pick? Intuitively, what seems to make most sense maybe is to pick the one that maximizes the distance between the convex hull of the 2 points. But this is just an intuition. This seems to be something reasonable to be doing. So that we'll be looking for the one that maximizes the margin between the 2 sets of points. So a little bit of notation and conventions for optimal hyperplanes, because they are exactly the ones that picks the solution that maximizes the margin. We will always be working with the so-called canonical hyperplane. That is, we normalize the vector omega that describes the separating hyperplane such that it produces the value of 1 for one class and -1 for the other class, for the points closest to the surface. This is just a convention. This is just a normalization. The distance between the 2 lines for -1 and 1 we'll call the margin, or actually it's 2 times the margin. The margin is up to here. And with these conventions, it's easy to see that the margin, or 2 times the margin, here is actually 1 over W. We can make a projection, 2 times the margin. It's the projection of this vector down on this vector, which gives us just 2 times the norm of the margin. So if we want to maximize, 2 times the norm of the vector, if we want to maximize the margin, it's equivalent to minimize omega. Okay? So that's how we end up with the constraint optimization problem. We want to minimize the norm of our vector describing the separating hyperplane under these constraints, that all the points should be correctly classified. So this is the cost function for the simple separating hyperplane. There are some very nice properties about this optimization problem. First of all, if a solution exists, it's unique. And, well, it may not exist, but if it exists, it is unique, and it's a nice convex optimization problem, so you can use your standard routines and know methods for solving the problem. Now, how do we solve it? Simply, we introduce Lagrange multipliers, non-negative Lagrange multipliers corresponding to all the constraints. We arrive at this Lagrange function, and it has to be minimized with respect to omega and e. So we can write down the Kutoka conditions for that. The minimum at the optimum, the derivative with respect to omega should be 0, and with respect to b, it should be 0. So we end up with these 2 expressions that the solution vector can be written as a linear combination of all the points with non-negative or with non-zero Lagrange multipliers. This is the constraint we get from that the derivative with respect to b should be 0. And then we have the complementarity conditions that for all the multipliers, the Lagrange multipliers, alpha I times this expression should be 0. Okay. A little word about the complementarity conditions. They actually give rise to what is called the support vectors. This we have should be 0, that is that either alpha I, the Lagrange multiplier, is 0, or this expression is 0. So either alpha I is 0, and that point doesn't even contribute anything to the solution. We can actually remove the point from our training set and we'll get exactly the same solution to our optimization problem. Or alpha I is not 0. That is, it lies exactly on one of these margin planes. Either it's in the +1 or it's in the -1. The points that lie on these 2 surfaces, those are the points that we call support vectors. Now, one very important thing that almost everybody gets a little wrong. The solution to this optimization problem is unique. The support vectors are not. The support vectors will tell you absolutely nothing about, the characteristic points of this problem. On top of that, these are actually in a way the outliers. These are the borders of the convex hull of the data. So they are not representative in a way of the data. But they are not unique. The solution is unique. Now, we can take the expression we obtained from the gradients and substitute it into our Lagrange function that eliminates omega and v from the function. And now we're left with this problem. Maximize this function subject to these constraints. And the solution we'll find is this form. The hypothesis on a given point given as the inner product with all the support vectors, and this is the expression for v. One thing you have to notice already here is that nowhere in these equations does an x appear on its own. It always appears in combination with another x. They're always in terms of inner products. You don't see a single x standing alone. So that is what we'll later make use of when we go to the kernelized version, that we actually don't need to know what x is in itself. We just need to know what is the inner product of x with another x. So far, so good, right? There's a little interesting note one can make about the support vectors. When we train a support vector machine, the number of support vectors actually tells us something about how well this machine will be able to generalize. You train maybe a linear. Now I know that you have trained a lot of things, so you train a second degree polynomial or third degree polynomial. Look at the number of support vectors. It will tell us something. The more support vectors, the worse it is. That can be found from an argument based on the leave one out error. Everybody in here knows what the leave one out error is? Yes, yes, yes. Who are the no's? Okay, we have some no's. A leave one out error is like a M-fold cross-validation. So you have M training examples. You take one out, you train on the rest, and now you test on the one that you have taken out. And you repeat that for all M options for taking out an example from your training set. That's the leave one out error. Leave one out. Okay? What is easy to show is that the expected value of the leave one out error is an unbiased estimate of the generalization error of this classifier. There's a little catch here. Actually, if you want to have the expected error of something that's trained on M-1 example, then you need the leave one out error for M example. So there's a little offset here in M-1 and M. So in general, if we want the expected error for a classifier based on the leave one out error, we have to look at the leave one out error for something that's trained on M+1. That's just a little tip. So how does that go then for support vector machines? Well, here we get to that the expected error for something that's trained on M points is then the leave one out error for something that's trained for M+1 points. And look here what I put in, the number of support vectors. Now that is actually a very easy thing to prove, because think about it. We trained this system, right? Now we've taken out one point. If that point we took out was not a support vector, well, it's not going to change anything to the solution, right? We're going to get exactly the same solution. The solution only depends on the ones that had a non-zero alpha. It wasn't even part of the solution in the first place. So we're going to get exactly the same answer as we got before. If the point we took out was a support vector, then maybe, not necessarily, but maybe we may get another solution. That is, we may get an error when we test on that point. So we cannot get more errors than the number of support vectors we have. So that's how we arrive at the little theorem that we get the leave one out error of the number of support vectors divided by M+1. That is, the more support vectors we have, the worse off we are.
Is there inequalities because of the non-uniqueness of the support vector?
Yes. The non-uniqueness, and actually, the non-uniqueness of the support vectors, if we could get a small set of support vectors, but that has always been a problem for us to find.
So it's almost as if the multiplicity of the support vectors or the redundancies is
Yes.
factored by Michel's argument.
Yes.
Okay.
Yes. So this was all I was going to say about the non-separable case. So this all worked beautifully. We have a little, we have an idea of the generalization error, and we know how to solve the problem. This all worked beautifully if the data is separable. But in real life, the data is not separable. What do we do? And that is where I started my thesis work. My job is simply find out what we do with support vector machines when the data is not separable. That I worked with Vladimir Batnik for a couple of years, and we came up with the following solution. Maybe we shouldn't be so tough, right? Maybe we shouldn't just demand that all the points should be correctly classified. Well, let's introduce a slack variable for all the points, right? We'll give them a little slack. They don't necessarily have to be larger than 1 or less than -1. We'll give it a non-negative slack variable each point. In doing so, we keep the same normalization conventions, and we preserve the same notion of emergent, but now it'll turn out that the support vectors are not only the points here on the right on the surfaces where we have is 1 or -1, but also all the ones that have a slack variable. Here we have the slack variable, right? This point here, we couldn't get that up on that line, so we gave it a slack variable. So it meets the sign, meets the criteria. This one also gets a slack variable. Well, of course, we don't want too many of these slack variables floating around. We don't want too many errors on our training set. So we arrive at the following optimization problem. We want to, again, minimize the norm of the vector, that is keeping the biggest possible separation between the two sets of points. And then we also want to minimize these number or these slack variables. And the constant c here, the non-negative constant c, controls how much we want to penalize these slack variables. If a solution exists, and it does depend on the value of c, you may choose c large enough that it doesn't exist a solution. Again, the solution is unique, and it's a convex optimization problem. Just a small word about our error function. It is an approximation. I mean, in reality, we would like to minimize the number of errors, right? But that doesn't leave us with a convex optimization problem. So instead, we use this hinge loss function, right? Here we have a point x that's lying right on the surface omega x plus b equal to 1. And it actually isn't an error until it gets past the line omega x plus b equals 0, where it changes sign. And the hinge loss actually already starts penalizing it on its way down to 0, and then it's always updating the 0, 1 loss function. You could, in alternative, also make use of the quadratic hinge loss. That's not as popular in SVMs because this one leads to a nicer optimization problem. But it is an approximation. So even if you see that you, for a given c, you lower the value of your cost function, it doesn't necessarily mean that you lower the number of errors, because there's a little difference between the hinge loss cost function and the true errors. Okay. Yes?
Optimizing the 0-1 loss function is NP hard, right?
Yes. You do want to do that. Well, you do. Maybe you do want to do it. But,
well, there's also a question about generalization if you do that. I mean, it still doesn't tell you which hyperplane to pick if you get a perfect classifier.
Right. Well, you could minimize omega under the constraint that you want to diffuse errors directly, right? But it is NP hard, and that is why we gave up on that solution. So again, how do we solve it? Well, we introduced Lagrange multipliers. We have the multipliers from before for the constraint here that they look a little different now. Now we have this slack variable, and then we also have a multiplier for each of the slack variables. So this is our Lagrange function. These are the topic conditions. Again, the solution will be expressed in terms of the vectors with positive alphas. We get this constraint from the b's, and then we get this additional constraint that the sum of alpha I plus beta I should be equal to 0. These are the complementarity conditions. So as you can see from the complementarity conditions, now we have two sets of points that have a non-zero alpha. We both have, or we have all the points that actually lie meet this criteria, but some of them will lie on the surface and some of them will have a positive psi. So it's all the points that lie between the surfaces or on the other side of the surfaces. Again, the support vectors are not really the solution. And if we substitute the expressions from the conditions back into our optimization problem, we get the following optimization problem. Again, a convex optimization problem where you can use all your standard tools and techniques. And actually it looks very much like the optimization problem we had before. The only change is now that alpha I is boxed in between 0 and c. And also the expression for b is only evaluated with the ones that alpha I is less than c. So that's as much as I'm going to tell you about the optimization problems for SVMs. Yes?
some of the slack variables seems to be artificial. I think we're looking for not to exceed the maximum instead of the sum, right? I'm talking about instead of the sum of all the CIs.
Yes.
Why not just use maximum?
Because it doesn't leave you with a nice optimization problem.
Oh, I mean, there are other tricks you can do to do that. But I'm just saying that is that sum of CI is that necessary, or I mean, it's just one?
It's just one, yes, it's one approximation to, but the max would actually not give you the same because you're not interested. I don't care actually what the max is, as soon as a point crosses over the surface omega x plus b equals 0, it's an error. I don't care how much it's an error. Right? In reality, I want to find the surface that has the biggest margin between the two sets of points and commits the fewest number of errors.
But why is sum? I mean, in that case, why do you use the sum of all the CI?
There's a nice upper bound of the number of errors.
Yeah.
You know, if you feel like using something else, be my guest and go through
I'm just trying to
the.
find a rationale. That's why we use sum instead of other constraints.
The max I would not recommend because you could have a lot of errors that would then, you would have if there's one really big outlier, that's going to give you an enormous max and it doesn't represent how many errors there are. Right? So, that's just, you know, it's a choice for getting an optimization problem you can solve, work with other choices.
But if you have one big outlier, it will also show up in the sum.
Yes, it will. But it will not. It'll also have.
And if you have a lot of points that just cross the boundary, then you will have a very small sum but a lot of error.
Yes.
So it seems that both choices have pluses and minuses.
Oh, both. I mean, all choices that are an approximation have problems. The nice thing about this choice is that it leads to a feasible computational problem. But it is an approximation. Yes. Again, in this approximation, you see that in this solution, we only have inner products, right? And x does not appear anywhere on its own. So that is one important observation to keep in mind. I'll come to another important observation, and that comes actually from theory about margin classifiers. The optimal hyperplane, as I said, it's sort of just our intuition, right? That it's a nice idea that we take the one that separates the points most possibly, has the biggest margin. But when the whole SVM algorithms, all these things we worked on them, we actually didn't have a good theoretical justification for doing it. That only came later on. In 1999, Bartlett and Taylor, they proved the following theorems. There are actually two here. One is for the separable case and one is for the non-separable case. Let me not go into too much detail about what is in these bounds, but these are bounds on the generalization error expressed in terms of the margin. So here we have, if we look at the one down here, because that's the one that's most relevant for us. Here we have the number of errors we made on the training set, that's B. Here we have R, which is the radius of the smallest sphere enclosing all the training points. Capital lambda here is a bound on the length of the vector that describes the separating hyperplane, the norm of omega. And what it says here is that the larger margin we can get, the smaller our bound on the generalization error becomes. So now we actually have a theoretical justification for doing what we're doing. Get the largest margin and you'll get the best bound. On top of that, you see here how the number of training examples enters the picture. And of course, if we can separate the points, we get a better dependency on the number of training examples. It goes down as 1 over m. Here we get a 1 over square. In general, the more examples you train on, the better bound you have, and making a trade-off between the number of errors and the margin on the data set. So one thing that is important to see in these bounds is that the dimensionality of the separating space, it doesn't enter anywhere. There's no D here in these bounds. It just says the margin. So that takes us to the next part of support vector machine. That's the justification for the kernelized version of it. So we have these two observations. The generalization bound, it doesn't depend on the dimensionality of the separating space. Okay, so why don't we just take our original points and via some nonlinear mapping throw them into some high dimensional space? As long as we can get a good separation up there, then we're fine. The bound tells us we're fine. But it's costly to be working in that high dimensional space. So that is where the second part comes in. In the solutions you saw for SVMs, we never actually need to work with the x in this high dimensional space. We only need to know what is the inner product between two x's.
Is it true that the dimension doesn't hurt you because the radius of the sphere, if you project it in some high dimensional space, aren't you likely to get a big radius there?
That you could argue that you are likely to get a bigger radius.
Right.
So you have to take both things into account. That is a very true observation. In general, it doesn't hurt you or anything, but you're right that implicitly it enters in the radius.
Also, the number of training points shouldn't increase with the dimension. I mean, the number of support vectors or the hyperplane dimension depends on that.
The number of points does not necessarily have to increase in order for you to get a good generalization ability, even as long as you can get them laid out in such a way that you get a large margin. You're not hurt by the curse of dimensionality, as you usually would be. As long as you obtain a good margin, but you're right under the, without blowing up the radius too much.
Let me ask you one more quick question about
Yes.
the previous theorem. So there was a thing that said that the bound on the generalization error on the right hand side has a B. And so in case of separable data, of course, we get B0.
It actually, in case of separable data, you can prove this stronger bound.
Okay, I guess my question was, okay, maybe the stronger bound takes care of my question. The question is, even in case of separable data, is there any gain to be had by letting a few things be misclassified?
Yes, because there'll always be errors on the data. Yes.
So, okay, so in other words, the simple demonstration you had earlier saying this is what we want, that's not exactly true. You may want to.
Well, you may want to make use of both things. Yes, we'll have two techniques now to obtain a good error. Either by you have to trade off between how many errors you're committing and what margin you can obtain.
Because if I just give up on one point and it lets my margin grow much bigger.
Then you are probably in good shape.
The margin depends, of course, on the definition of some distance dimension, right? So, I mean, then it depends on the dimensionality in some sense, because it really depends on how you construct the distance dimension.
No, not if they lie. You need the distance between points, the closest points in the separating space.
Yeah, but I mean, we're talking about Euclidean space, but it can be other space.
If they are projected there, if they lie in a low-dimensional manifold of your high-dimensional space, then it's 0 for the rest of the coordinates. You don't have to worry about it. It doesn't enter your row. Okay. Any more questions? So we have these two okay, this side. D doesn't explicitly enter the generalization bound, and we only need to know the inner product between 2 points in this high-dimensional feature space. So that is where kernels come in as the saving grace. They will provide a closed form for implicitly calculating the inner product between 2 points in the feature space. So let's define a kernel. So here we have our phi of, we have 2.2 x, and do not be confused by this is called y now. This is another point x, and we throw them, we take our nonlinear mapping phi and put them up in some high dimensional feature space where we need to compute the inner product. We'll define a kernel K if it can, in a closed form, compute the inner product between two vectors out in this high dimensional space. So you can think of it as a similarity measure because that's actually what an inner product is. It's a projection of 2 points onto each other. And it will be much more, in general, efficient to compute an inner product this way than that way. And it gives us a lot of flexibility for how to construct our nonlinear mapping. Let me just give you a little example for how much more efficient it can be to compute an inner product this way. So here we have an example, a polynomial kernel. Let's take the example of a second degree polynomial. The ones of you that have trained SVMs using any standard software have probably made use of either a polynomial kernel or a Gaussian kernel. So you set the parameters, they just use a polynomial and d equal 2. Now, so the inner product between 2 points x and y, if you write it out for a two-dimensional space, it is actually just this expression. Now this is equivalent to taking the inner product between these 1, 2, 3, 4, 5, 6-dimensional vectors. The solution is the same, whether you take the inner product of these or you just compute it like this. So if we were to do it explicitly, throw our points into the nonlinear feature space where we would be doing the linear separation, we would have to blow up our points from being two-dimensional to being six-dimensional, and when we have to compute the inner product, we have to do it this cumbersome way. That we get rid of by making use of the kernel instead. And we may be lucky on top of that, because problems that were not separable before may be separable if we apply a nonlinear mapping. Let's take the simple example of an XOR in 2 dimensions. Here we have XOR. We want to classify these 2 points as being in the same group and these 2 points as being in the same group. Now, obviously not linearly separable. What can we do? Well, if we make use of the feature mapping from the previous slide, here I just show you 2 of the coordinates from the previous slide, the x1 and the x1, x2. Now it's all of a sudden separable. So actually, just making use of a nonlinear mapping turned our otherwise non-separable task into a separable task. So, as I said, we have 2 ways now of combating non-separability. We can either make use of a kernel trick, throw it into a space where it's hopefully separable, or we can allow for slack variables. Often we want to make use of both because there will be error on the data, and you have this trade-off for how many. Well, first of all, we may not know what is the optimal mapping. Here it's brilliant, like we just by a miracle find the right mapping, but that's often not the case. So we can play around with these 2 to see what gives us the best generalization. Can we make use of any kernel? No, we cannot. Kernels, in order for this optimization problem still to have a solution and a unique solution, they have to be positive, definite, symmetric, or they have to meet Mercer's condition, which is equivalent to saying that the kernel matrix computed over all the points has to have only non-negative eigenvalues. And here are just some standard kernels that you find in all the standard software libraries. The Gaussian kernel, that is PDS, and the sigmoid kernel, alpha and A and B here have to be positive. Okay, so these are sound kernels that ensure that your optimization problem will converge into its unique solution. Feel free to use other kernels also that may not be PDS, but there's no guarantees for where you end up. Now, these kernels kind of implicitly assume that you have some fixed length input, right? There's an x and a y. But in real life, we don't have fixed length input. Just think of the speech data, we have computational biology, we have sequences, we have distributions over sequences. So what do we do? So that'll take us to the next part of this tutorial, rational kernels. So we hereby leave what I would consider the hard part for you probably, and go to what is probably more the easy part, because now we get into a world that is maybe a little bit more familiar to you. It wasn't to me originally. So rational kernels. So I should say, any questions at this point in time? SVMs, now you know everything about SVMs. Don't ever forget that the solution is unique, but the support vectors are not. That there are two ways of combating non-separability. That you can either make use of a kernel, or you can play around with how much price you pay for an error. And if you want to change the cost function to have another approximation of the number of errors, then maybe it's a good project for the next PhD thesis. But otherwise, we'll move over to rational kernels. Rational kernels are constructed from weighted finite state transducers. Now, how many have heard that word before? That is almost everybody. So it's a little bit harder than for the SVMs. So maybe it will actually be easy practice. Here you have an example of one. And as you say up front, we are going to sort of stay in plus times here. We're not going to do anything other simulations. It's just going to be plus times. So here we have a weighted finite state transducer. It has an initial state, it has a final state, and it has a number of transitions. Each transition has an input symbol and an output symbol and a weight associated to it. And in order for us to find the weight that this transducer associates to an input and output string, a pair input-output, we sum the weights of all the successful paths that allows this input x and output y, and the weight of a path is obtained by multiplying together the weights along the path. And there's a final weight. So in order for us to find the weight that this transducer T assigns to the input string ABB, output string BAA, we have to find paths that have ABB as input and BAA as output. So we have let's go with this one first. A as input, B as output, then we have B, A, that's one here, right? And then BA, and then a final weight of 0.1, so that's the weight of the one option for having this input and this output, and there's another option also that this one, and this thing. So the total weight this transducer assigns to the input string X, output string Y is the sum of these two products. Okay? Now, as I say, when we go to computational biology, text and speech processing, we have a lot of variable length input streams. So if we want to do anything with SVMs, then we have to somehow define kernels or similarity measures between these strings or distribution over strings. You get a lattice, right, as an output from a speech recognizer. So we have to find a way of defining kernels between lattices or between strings. And let me just give you an example here for how weighted finite state transducers may help us in doing that. If you think of that, the similarity measure may be expressing some commonality between the strings. How many common substrings or factors we find in these strings? Let me show you how we can have an FST help us compute these things. Here is a very simple transducer for computing or counting, computing the count of the appearances of bigrams in a very small alphabet with strings over A and B's. So here we have, imagine you have this long string of A's and B's, and now we can come along here. We can stay in the initial state, skipping as many A's and B's as we want to, outputting nothing, outputting epsilon, and just multiplying the weight 1. Now if we see an A and B, we may also decide on taking this transition, outputting an A, take this transition for an A, outputting an A, and then skip the rest of the string. So we will, because we can, for every time we say an A, we can either stay here or we can take this transition. We will be able to count how many occurrences of AA we have, AB, BB, and BA. So this transducer, if we compose it, if we apply it to a string of A and B's, will output 4 strings, AA, AB, BA, and BB, with the counts, because we get a count of 1 every time we go from the initial to the final. It's just 1 multiply. So this transducer will give us the strings, the bigrams with multiplicity when it's applied to a string. So rational kernels are simply kernels that can be expressed as a weighted transducer. That's going to be our definition. And as you can see, they can compute probably some meaningful measures or features for a similarity measure. Now, remember, it's not all kernels that we can use with SVMs. There is a criteria that they have to meet, right? They have to be positive, definite, symmetry. Anything that can be expressed as a weighted transducer, is that necessarily PDS? No, of course it's not. Let's go back to the example from before. So here we have our string A, and we have our transducer T that counts the appearances of bigrams in A by composition. Composition, how many know what the composition algorithm is? Are you composer? That's a little bit. Okay, so it's pretty much, it's very straightforward. A composition with a string with a transducer is that you're just lining up all the string, the input of the string, or the input of the string matches the input of the transducer. And you sum up all the successful paths where the string symbol matches the input symbol of the transducer. That's a standard algorithm for doing that. So we can apply the transducer I showed you before for counting the bigrams to the input string A. Now we wanted to have a similarity measure between 2 strings A and B. So if we kind of want to right apply T to the string B, well, that's the same as we're swapping what is input and output for the transducer. So that's what we just represent as T minus 1. It's called the inverse of the transducer. So now if we want to compute the sum of the products of the similar bigrams in A and B, we just have to compose A with T, T minus 1 with B, and then compose this whole thing together, composing 2 transducers with each other, also by matching up the paths where the output of the T transducer matches the input of T minus 1. So we end up with, since that again gives us transducer, we end up with a transducer between A and B, or a rational kernel. And what we can add to our definition from before is that actually if we construct a rational kernel like this, then it's guaranteed to be positive symmetry. Positive, definite symmetry. So here we can make use of any transducer. Take a transducer, compose it with its inverse, get a rational kernel that is guaranteed to be a PDS kernel that we can use as a similarity measure between our input string A and our output string B, and use that as a similarity measure in the SVM. Remember, we only needed to know what is the value of an inner product between 2 inputs. Now the inputs are not vectors, now the inputs are strings or lattices. So,
is the converse true? Is every positive definite symmetric rational kernel expressible as
that is a
PDS?
very good question. We conjecture that it's true. We haven't been able to prove it so far. Because one reason we conjecture it is based on some closure properties, but another thing is that all the kernels that we have found in the literature over the last 5-10 years, they can actually be expressed as these TT minus 1. If you take all the papers you've seen in computational biology from computer science people, they come up with a similarity measure. And if you sit down and work through the details, you can see it can actually be written as a transducer T minus 1. If you find an example of a paper where it cannot be expressed as that, I would be very happy to see it. But at least these are examples of kernels that we have found in the literature, all beautiful T minus 1. Now, so what? Where the problem is that these people that have written all these papers, they spend an enormous amount of hours and pages, save the rainforest, in coming up with algorithms for computing the inner product between the two streams, and for finding good data structures for representing their streams. They don't have to. They can simply represent their data as transducers and a kernel as a transducer. And then they can make use of good existing, well-studied algorithms, and then focus all their attention on constructing good similarity measures. And of course it's the harder work maybe. I should say that these are the algorithms that exist, and of course you can, for special cases, maybe make it more efficient, but in general there is a quadratic complexity, or linear in each of the inputs, and then we have a fixed cost view here for computing once and for all the similarity measure. So now that we really have to focus on constructing the kernel, the similarity measure, we'll also see how easy it is in this representation. Let's go back to the example that we had before. This was the one that counts the occurrences of bigrams in the stream. Right? So say now that, well, maybe the two parts do not have to be right next to each other, right? We can have an A here and we can have an A here, but there's sort of we'll skip a number of symbols in between, but we'll pay a penalty, a Gabi engram, right? How hard is that for us to make it in this framework? Which is very, very simple. We just insert an extra little loop here. Skipping whatever we want in the middle. Paying a price of lambda is how we do it. All we have to do is put this kernel into our computation instead, and we're set to go. It's almost as simple as changing the D in your polynomial kernel in your libSVM. So that is about the general framework of rational kernels, where I just urge you to think of deciding instead what is the similarity measure you think appropriately captures the similarities or lack of differences between these two lattices. What are the features that characterize our data? Don't worry about the algorithms for computing. They exist out there. They are implemented. I have good news for you also. We are releasing a new library. It's an open source library, joint work between Google and NYU, as you can imagine. It replaces FST, the FST library. I think it's now called FSM. Yes. OpenFST.
It used to be called FSM.
Oh, so before it was FSM, and now it's going to be called OpenFST. As far as I know, it is out there. I'm sure you can find it, if nothing else, with the help of this gentleman over here.
I think by doing a Google search.
By doing a Google search. I don't know, because it's actually linked under NYU, so it depends on how high up it is. But I'll make sure that we link it from Google, and then we'll probably get it very easily. So there's that, and there's another open source library on its way, also joint work between NYU and Google for kernels. So there'll be some of your standard kernels, and you can interact with. Yes?
So I have a question. Maybe you're going to get to it soon, but one of the The other nice things that we like about finite state machines is that there are training algorithms for instance, learning this lambda. But when you're embedding it within a support vector machine, generally people are not. There doesn't seem to be the obvious backpropagation algorithm to learn that lambda inside the rational kernel
Where there
from
is
data.
that is it's an open research problem, how to learn the kernel that will best separate your data.
Right.
That is actually not something that is in either library right now, in any library all over. Right now, all you can do is trial and error, right?
Right. Well, or you could learn a generative model.
No, you cannot learn a generative model, I would claim, because you can learn a generative model of your data, but that's not necessarily the kernel that will give you the best generalization ability.
Right, it's not going to optimize the problem.
Yeah. How to learn a kernel is a much harder problem. It's a very good problem to be working on, and you see a number of papers coming out in that direction. Every NIPS will have a couple of papers on how to learn the kernel.
But nothing specifically for rational
No.
that you're going to
No,
talk
no.
about.
Once you solve the problem in general for how to learn the kernel for a classification problem, then we'll make sure that it also gets implemented in the libraries. So now that you know what rational kernels they are, and hopefully soon we'll have the software for playing around with them, I'll show you some applications to speech and computational biology. This was, of course, done with the old libraries back at AT&T. Our results. So we start out with spoken dialogue classification. This is the "How may I help you" line, where people are calling into customer reps to complain about their billing issues or service issues. And here are some of the data sets. We have a large number of classes, 64, 97, 82. These are the categories of complaints that people can call for change in address, billing service. It is actually really deployed. It was trained on the training exercises, and it's really, really ugly data. You heard a little bit about it in the beginning. I'll give you some more examples for how ugly it is. Some of the problems is that we have to be able to do it real time. This is not something that we can go away and do. I guess from this example.
Yeah.
So he's been,
Can you play it again?
yeah, let me see if I can know how to get it back on. Okay. I don't think it's gonna stop. He's waiting for the computer to respond to him. I think we screwed up everything completely.
I want to know why my account is past due.
We don't know what this background noise is. It's not the computer chunking along, but you
This
could
is
think.
bizarre. They actually have a computer that says, "Hi, I'm an automated AT&T operator. Please speak clearly. How can I help you?" Yeah. And I said what I had to say, and so far they haven't had any response.
So that's of course not the situation we want to be in. Real time is a true problem. The next problem we have is that this is a classification task, so we have to find out which of these 97 categories we have to route it off to, and that can also.
I want to know why my
If I speak naturally, to you, you're going to tell me you don't understand. I'll speak naturally, and I hope you understand. These automated calls aren't worth a lead nickel. Anyhow, I want to find out if I place a call to area code 1-440-526.
I think it's all confused. We've managed somehow successfully by going back and forth to get them all to go on top of each other. Anyway, there's one more I would have liked to play for you. But what you saw with the classification problem is a little bit that it takes the customer a long time to get going. And it may never actually state clearly what the problem is. It's like, I just want to know if I place this call into 4-1 something. And obviously it's a billing issue she has, but that's not ever expressed clearly in the statement. Then comes the variability in speech, and I don't know if we can now get this working or we cannot get this working. This one we have the transcript for, so it tells you how badly we recognize the single words.
I want to know why my account.
No, we give up on that one. It was horrible anyway. Somehow I think we should turn this one down again. Yeah, mute it out, because otherwise, I'm sorry, I'll play them for you later if we can get the computer working in a more normal fashion. It's absolutely, totally difficult to make head or tail out of what people call in. Just think of yourself when you're calling, you get confused also about what am I going to say to this one. So the input we had was the output of the speech recognizer from AT&T. It's word lattices. So now it's not just one string, but all the or a set of strings representing the best possible transcriptions of this utterance. And the algorithms that we made use of was rational kernels. We made use of trigram kernels, so now it's not bigram, but trigrams, commonly occurring trigrams in between two lattices. And that was the first one we made use of. Then we made a variation. We actually not only looked at the count, but the variance in the weights associated to the paths. So you can have that all the paths that they have about the same weight for a string, or you can have or for a trigram, or you can have that these weights, they actually come with a large variance that you can expect tells you something about maybe not what task, but the accuracy with which you can derive what task it is. So we had a variance kernel. I'll show you that one over. And we the classification we took was the max output. So we take whatever classifier of the 97 classifiers produces the largest output. That's the classification. And as I said, this was all implemented in the old AT&T, but hopefully soon we'll be able to move it over to the new libraries. So this is just a comparison for how we did, and of course we did better, because otherwise I wouldn't be given this pitch for rational kernels. Standard techniques from AT&T at least was boost texture, where you're boosting on the occurrences of the phonemes in the lattice. That is our baseline. Here we have a rejection curve, the error rate as we reject more and more of the data. And so you start out by just keeping everything, and then you get more and more certain about what you keep, and therefore you lower the error rate. And so this was our baseline. And here we used the rational kernels, just the trigram kernel on the one best path of the lattice, and then we went to using the whole lattice, and you can see that it's definitely a gain, not just using the best one, but using the whole lattice. Obviously, the path with the highest weight may not be the correct path, but the right path may be just in the top, whatever top end. So you may be able to get the right classification by using the full lattice, and that is what we see here. Can you barely see that green line from back there? So this is the results on how may I help you 03 record, and we have similar.
Can you what it means? So let's say I'm at the 60% rejection rate, so
Yes.
my error rate is 5%.
Yes.
So what it means is that the calls that I don't reject, 95% of them get routed correctly. Is that
Yes.
what it means?
Yes.
So what happens to the 60 that are rejected? You ask them to repeat, you hand them to an operator?
You hand them to an operator.
Okay.
You probably let them first go through the tedious experience of repeating and again saying, I cannot make head or tail out of what you're saying, and then you send them to an operator.
So by then they're thankful that they're
By then they're really, really upset, right? so actually there was another project that I remember Mario, he was involved in at AT&T, where they were trying to find out how angry the customer is. So, and you can do the same thing, right? You can do it based on the words, the phonemes, trying to build kernels, or just use bigram trigrams to determine how angry they are. And that was obviously where that was going to be used. And I think they ended up getting some reasonably good results from that, the sentiment analysis work they did. So the results, how may I help you? We of course do well on all the three data set that we made use of, voice, tone, one. Again, we're beating, the color coding has changed a little bit. So
green and blue.
yeah, they're switched. Complain to Patrick about that one. And to voice tone. So again, we managed to go above or below an error rate. This seems to be a much harder task, right? Voice tone also has many more classes, and more classes you have, the harder the problem becomes. So we made this extension also, as I said, we looked at the variance and how much weight is associated to a given engram in the lattice. Does it always come with about the same weight over the various paths, or does it come with a variance? And it turns out that you can also compute the variance using a transducer. And I'll just show you a picture of the transducer. It looks pretty, right? It's a little bit more complicated to deal with. We made use of it and got additional speed or additional performance improvement, 1% and 15% reduction of age. So that is the current state of the art, at least from AT&T on how may I help you, and automatic real-time recognition of how to route the calls. So this is one application of rational kernels, and then in the remaining 5-10 minutes, I will just say a few words about computational biology, where we also see a lot of these instances. Unless I should take some questions here. Okay. So here we have one of the problems that have been looked at a lot in computational biology. There's a data set that's called SCOP, and the task is to categorize protein sequences into families and superfamilies. There are 33 superfamilies, and to give you an example for what the data looks here, we have our strings. It's not distribution over strings, but we have all these amino acids lined up in entry sequences, and these are two positive examples for the particular class of anybody who wants to pronounce this one. And here we have some negative examples, protein sequences that do not belong in that family. There's a snake that at least I can see, and this is publicly available data sets that you can go with. And a lot of people have been playing with it. One person that has worked in the area is Christine Leslie from Columbia University. She came up with this mismatch kernel, where you say that two strings are similar, two strings of length k are similar if they're no more than m apart from a common ancestor. So this is...
Say it again, please. They are similar if what?
If they get a count of 1, if they are no more than no more of m of their positions differ from a common ancestor. So there is some common ancestor. This one has moved not more than m away from it. This has moved no more than m away from it. But it can be any common ancestor. Well, it cannot be any common because it has to be less than m away from this one and less than m away from that one and have something in common. So they spent a couple of papers on finding out an efficient algorithm for computing this mismatch kernel and for how to represent the data. Well, lo and behold, we can also do that. Very easily, here is a representation of the t part. So this is just half of the kernel, and we'll have to combine it with t minus 1 to get the full kernel for an alphabet of size 2. And here what you see is for the case where it's sequences of length 3 that are no more than 2 apart from a common ancestor. And every time you go horizontally, you match up completely. Every time you take a diagonal, you make one error. So if you want to make no more than 2 errors from the original sequence, then you're allowed to take at most 2 of these diagonal paths. These are the final states. This is the initial state. So you can either, you can make your way through the grid in any way you want, making no more than m differences. Yes?
But they're all the same, so all the weights are 1,
Yes.
no matter how many errors you make.
Yes. That was the choice that she made. You could, of course, now that you have this simple representation for it, you could much more easily play around with penalizing errors in different positions differently. Yes. But this is the transducer that represents her mismatch kernel, and you combine that with t minus 1 to get the final transducer for the whole thing. And she got very good results with, or not very good, she got better results, at least that here was the baseline they started out from. This is an RC curve for their results. They used Fisher kernels also. This is the blue line, but their mismatch kernel 5-1, so they have sequences of 5 that are only allowed to deviate in one position from a common ancestor. That is their best results, where they have the RC curve here. There's another example here from computational biology. Recognition of translation initiation sites. So these are DNA, not all parts in DNA sequences, they have the same meaning. So here they're trying to locate where in a DNA sequence could be a translation initiation site. This is work done by Peterson and Nielsen that looks actually almost as distinguished. They have about 13,000 sequences and 3,300 true sites to classify from whether this is a translation initiation site or not. They made use of a kernel much more like what you're suggesting over here, that you have 2 sequences of lengths x and y, but you pay a different price whether the match is in the same or where in the sequence the match is. So you can imagine that you have your 2 sequences, they are lined up, and you want to count it as a high similarity if they match in the middle, but lower similarity if you go out to the sides. Just a suggestion. Again, it turns out that we can represent their kernel with a transducer. Here's just, it's a corner of the transducer, but here you see we match, so in over an alphabet of size 2, we match A with A with A, and we get the full weight, W1, W2, W3. If we make one error here in position 3, then we only get W1, W2, etc., etc. You would have to also plot the similar for if the input symbol started out being B. But here we start out by making an error in position 1, then we make it right, and then we make it right again, and we get therefore the weight W2 plus W3. Again, most of their paper is dedicated to the algorithms for computing this kernel and an efficient way of representing the data. Spend the time playing around with the kernels, that's what we encourage. So these are 2 examples of kernels that we've seen successfully being used in computational biology. And we're not saying they're bad kernels, we're just saying that there's a general framework where you get all the algorithms for free, and you can focus all your attention to constructing a good similarity measure. So other kernels that we have come across that fits into this framework is mismatch kernels, as you saw, convolution kernels from Hausler, path kernels, also out from UC Santa Cruz. The edit distance, we can easily come up with a transducer that represents the edit distance. The edit distance is not PDS. It does not come in the TT-1. We have actually examples of it. It's not PDS. So please do not use the edit distance in combination with SVMs because there are no guarantees for where you end up. Well, you can use it, but you just don't know where you end up. So that is about what I say for applications. We are almost out of time also. I just want to end with a few theoretical results you asked before. Is it such that all PDS rational kernels can be written in the form TT-1? We don't know yet. We conjecture that is so because we haven't found examples of PDS kernels that are not, and because also there are closure properties of the TT-1 kernels that match the closure properties of some positions that could make us think that they are all of them. But that is still something to be proved. Do I have to, I guess? I'd be happy to work with you on it. We started asking other questions like, if I have a rational kernel, what is the set of languages that are separable with it? I think it's an intuitive, you have your kernel, you can write it down, but what's that set? And even if we manage to, so we have a way of at least giving you some characterization of the language that it can separate, but will we obtain a positive margin in the separation? Is this a kernel that will guarantee us a positive margin and hence a good generalization ability? It is not always the case. They have to be finite range kernels, and how to construct a finite range kernel from your original kernel is not that straightforward, but we have an algorithm for doing that as well, which I hope will also be part of the library at some point in time. So anyway, I'm going to conclude here with a few words. I hope I have convinced you to make use of rational kernels in combination with SVMs for all your classification problems you may have. It's a nice unifying framework that leaves you free to worry about the design of the kernel and not the algorithms and the representation. Definitely, so far we haven't seen any examples from computational biology that couldn't be handled with rational kernels. We have, of course, a good theoretical foundation for making use of them with SVMs. We have the Kernels that still hold. And they're just very easy to play with because you can visualize them, right? You can easily see, oh, it makes more sense maybe to change here versus there. You can plot your kernel and see if that seems to be doing what you think it should be doing. It's of course up to your imagination and creativity to construct a kernel. Hopefully one day we'll be able to give you a good algorithm for learning the kernel, but that's also an open research problem. So that's where we end.
Questions?
Yes.
You developed this theory based on two-class problem, right? But I mean, what can you say about cases with more than two classes? So that's the first question. And then the second one is you have many applications that talking about more than two classes. So what did you do to make it generalizable to multiple classes?
Multi-class problems you can solve in at least two ways, right? you can always train a classifier for each of the classes where you train it as one versus the rest. Or you can try to divide it up and train it in a hierarchy, so you split your data, right? You're first going to train these classes against these classes, or you can, for that matter, go all the way down to train them pairwise, right? There are pros and cons for all these approaches. There are definitely people at Microsoft that would say it's much faster if you want to train an SVM to do all pairs, because you have less data to train each classifier with, instead of you do one versus the rest, because then you have a lot of data and the runtime of your problem is probably not sublinear. We have in all these examples, we've done one versus rest, and then take the max of these outputs.
So you run into the situation that you have very few positive examples, but a lot of negative examples.
Yeah.
Would that be a problem?
No, it's not a problem. I mean, it's better than if you do pairwise, because then you have just very few positive and very few negative, right? At least you get a better description of where the negative space looks like when you have all the negative points, but you have to pay the price in training time.
I wonder if you aren't also paying the price in terms of generalization error, because now the volume of the data is bigger.
I don't think that there are any studies that say that you get a better by training one way or the other. I mean, one thing is the bounds. The bounds are always an inspiration for us for what to do, but they are not always tight bounds. At the end of the day, it boils down to how well did you do experimentally, and that's where I think that there are no experiments that says always do pairwise, always do.
How do you choose the C constant?
Cost allocation. That is so far the best way we have to do that. Yes?
Seeing those automata you showed us, I wouldn't, I mean, if you get the kernel and then you want an automata, I see how you would do it. But I mean, the automata don't seem to be a straightforward way to manipulate those things. So, would you say that those domain-specific languages you have for kind of manipulating weighted finite state transducers translate nicely to a domain-specific language for kernel design, or do you have to make up something different, or just have your own ideas about this?
Do you mean should she have expressed those machines in terms of regular expression?
Well, should yes, definitely, and would it look nice?
I think pictures, they look much nicer. That's what I work with the best. That's for sure. I guess it's an individual choice, right? What do you want to do? I don't think there's a general answer to that question.
I mean, not look nice, but look nice in the sense that you have a firm grasp of what it's doing just by seeing the expression. While in those graphs, I had the feeling that I have to walk each path and then go through the loops and then see, oh, that's what it's doing.
As a matter of taste, I think it's a matter of training. I looked a lot of these, and that seems the most intuitive way for me to represent it. We may all have our favorite eyes, right, in our background, like I said. To me, it's much simpler, at least, to look at a picture like this than these complicated expressions that we otherwise get when we especially something like this, right, where you get, this is the similarity measure, right, and then you have to often look in the text, like, exactly to find out how Z was defined, relative to Z1, and then I think at least a picture with transitions you can understand. This is where you go with when it's matching, and this is when you go where it's not matching. That's much more intuitive, but it could be that your training makes it better for you to look at other kinds of expressions.
I think we just thank you.